The cosmic event horizon sits at 16.7 billion light-years from Earth, a number in the equations of modern cosmology that defines the cosmic microwave background era and Lambda-CDM model we observe today. It is not a constant pulled from a textbook. It is not a value that turns up on the front page of a popular science article. It is a distance, a measurement of how far light, given the entire infinite future to travel, can ever reach you again from this moment forward. And the number says that for every observer, on every world, in every galaxy currently visible in the sky, the answer is finite. It has a maximum value. Almost everything you can presently see is already beyond it. You are not looking at a universe you can explore. You are looking at an archive. The light arriving in your telescope tonight from objects 10 billion light-years away was emitted billions of years ago by regions that in the present moment are causally severed from you. You can see them, you cannot reach them. You cannot signal them. You cannot affect them. The mathematics says that every wavefront leaving your location right now, traveling at the absolute speed limit of physics, will never overtake the expansion of space between you and them. Those galaxies are visible only because they were close enough, long enough ago, for their old photons to still be in transit. Once those photons arrive, the conversation ends. There will be no second message. This is the cosmic prison. It has no walls. It has no bars. It has no warden you can identify. The prison is built into the geometry of space-time itself. And the latest measurements from the Dark Energy Spectroscopic Instrument and the European Space Agency's Euclid mission only sharpen the diagnosis. The measurements reveal a 7.1 sigma tension between local Hubble constant measurements of 73.5 kilometers per second per megaparsec and cosmic microwave background-derived values of 67.4 kilometers per second per megaparsec, a discrepancy that affects our understanding of the prison's future architecture. The prison is real. The prison is permanent. And the most disturbing feature of the prison is not its existence. It is what the prison eventually does to the evidence. Take a moment to absorb the scale of what physics is reporting. The present cosmic event horizon, calculated from the parameters Planck measured between 2009 and 2018, sits at approximately 16.7 billion light-years from this location. That is roughly 1.58 times 10 to the 23rd kilometers, or 9.81 times 10 to the 22nd miles. A distance large enough that human language barely manages to convey it, yet a distance that is finite, measurable, and shrinking in co-moving terms with every second the universe accelerates. The Hubble radius, the surface at which galaxies are receding from you at the speed of light, sits a little closer in, at about 14.5 billion light-years. The particle horizon, the maximum distance from which any light has had time to reach you since the hot early universe, extends to about 46.1 billion light-years. 3 different boundaries, 3 different meanings. In a flat, lambda cold dark matter universe, only one of them is the final wall. In 2007, Lawrence Krauss, theoretical physicist at Arizona State University, and Robert Scherrer, cosmologist at Vanderbilt University, sat down to calculate what the universe will look like to intelligent observers in the very far future. The calculation was quiet. It was not designed for headlines. It used the same equations any graduate student uses, the same parameters NASA's WMAP mission had refined, the same expansion law that Edwin Hubble had identified observationally in 1929. They ran the equations forward. What came out of those equations was the most disturbing result in 21st century cosmology. The abstract of their 2008 paper, published in the International Journal of Modern Physics D, contains a sentence that should haunt anyone who reads it carefully. They wrote that, in the extrapolated future, all evidence of the Hubble expansion will disappear, and that future observers will be, in their own words, fundamentally incapable of recovering the true large-scale history of the universe. Read that again. Fundamentally incapable. Not difficult, not expensive, not requiring better instruments. Incapable. The cosmologists of 100 billion years from now, if any exist, will look up at a sky containing only the gravitationally bound remnant of the local group, a single merged galaxy where the Milky Way and Andromeda used to drift past each other. They will see no other galaxies. They will see no cosmic microwave background, the relic radiation Penzias and Wilson stumbled into in 1965 at Bell Labs in Homedale, New Jersey, the radiation that won the Nobel Prize in Physics in 1978, the radiation that anchored the entire hot Big Bang model of cosmology. They will see no redshift relation, because there will be no external galaxies left to redshift. They will see, in short, a universe that looks exactly like what astronomers in the early 20th century thought our universe was. A single island of stars surrounded by silent, eternal darkness. Here is the part that changes the meaning of every cosmology textbook ever printed. That future picture will be wrong. The universe will still be expanding. There will still have been a hot Big Bang. There will still be other galaxies racing away beyond the horizon at speeds that exceed any signal they could ever send back. None of that will be visible. None of that will be inferable from local data. Observers of the far future will look at a cosmos that lies to them by omission, and they will, with full scientific honesty, conclude that they live in a static, eternal, single galaxy universe surrounded by void. A view that in the early 20th century was already considered and rejected because the evidence said otherwise. In the future, the evidence will be gone. What does it mean that science can be permanently fooled, not by deception, but by geometry? This is not an abstract problem for physicists to solve in their offices. This is the fabric you exist within, the vacuum surrounding you, the space your thoughts occur inside. The same accelerating expansion that pushes the most distant galaxies past the horizon is pushing on the air between your hands. The effect is too small to feel. The implication is too large to ignore. You are sitting inside a cosmic apparatus that is, slowly and silently, reducing the amount of reality any observer in your reference frame can ever access. The prison is not coming for you. You are already in it. The only question is, how much of the universe will still be visible from your cell on the day you finally try to look? By the end of this exploration, you will understand what the cosmic event horizon actually is, and why it is not the same as the Hubble sphere or the edge of the observable universe. You will see why the equations of lambda cold dark matter cosmology force the existence of this barrier, what dark energy has to do with it, and why every attempt to identify what dark energy actually is has so far failed. You will see what Krauss and Scherrer's calculation reveals about the future erasure of cosmological evidence, and what the data from the Dark Energy Spectroscopic Instrument and Euclid are showing right now in 2026. And you will see what this entire structure tells us, when examined honestly, about the assumptions hidden inside modern physics, and about the conclusions that follow when those assumptions are tested against what the equations actually require. If you find value in explorations like this, in following the deep puzzles that keep working physicists awake at night, consider subscribing to the channel. It helps these long examinations reach more curious minds. Now, let us begin. The standard model of cosmology, the framework that virtually every working astrophysicist uses to interpret data from the James Webb Space Telescope, the Atacama Cosmology Telescope, and the Vera Rubin Observatory, is called Lambda-CDM. The lambda refers to the cosmological constant, the term Albert Einstein originally inserted into his field equations of general relativity in 1917, and later removed, calling it his greatest mistake. The CDM refers to cold dark matter, the unseen mass component that holds galaxies together against their own rotation. The model itself describes a universe that is spatially flat to within a fraction of a percent, expanding from a hot and dense early state, dominated today by dark energy at roughly 70% of the total energy budget, with cold dark matter at about 25%, and ordinary matter, the kind that makes stars, planets, and people, at less than 5%. Most of the universe by mass energy is composed of substances that have never been directly detected. The Planck collaboration, using data from the European Space Agency's Planck spacecraft, which launched on May 14, 2009, and operated from the second Sun-Earth Lagrange point, published their final parameter analysis in 2018. The headline numbers are these. The Hubble constant, which sets the present rate of cosmic expansion, came out to 67.4 plus or minus 0.5 kilometers per second per megaparsec. The matter density parameter, called omega sub m, came out to 0.315 plus or minus 0.007. The age of the universe came out to about 13.8 billion years. The geometry of space, on the largest scales, was found to be flat to within about 0.4%. The collaboration reported, with characteristic understatement, no compelling evidence for extensions to the base model. The standard picture, in other words, fits the data. It fits the data. It does not explain the data. This is the first foreshadowing point of this exploration. We will return to this assumption later. Keep it in mind. The mathematical model that describes the universe with extraordinary precision is dominated by two ingredients: dark matter and dark energy, whose physical identities remain unknown. NASA's own dark energy educational materials state the situation with admirable clarity. They say of dark energy, the short answer is, we don't know. The model works. The model is incomplete. To understand the prison, we have to be precise about three different boundaries, because in casual cosmology discussions, they are constantly confused. And that confusion hides the actual structure of what is happening. Tamara Davis, cosmologist at the University of Queensland, and Charles Lineweather, cosmologist at the Australian National University, published a paper in 2004 titled Expanding Confusion that mapped these distinctions carefully. Their work has become a standard reference for anyone trying to discuss horizons without descending into popular science nonsense. The three boundaries are these. The particle horizon is the distance from which light has had time to reach us since the hot early universe. It marks the edge of the observable universe in the literal sense. Beyond the particle horizon, no photon emitted at any point in cosmic history has yet arrived. The particle horizon today sits at about 46.1 billion light-years. That is approximately 4.36 times 10 to the 23rd kilometers, or 2.71 times 10 to the 23rd miles. The particle horizon grows over time because more light arrives every second from regions that were previously unobservable. The Hubble radius is the distance at which galaxies in the Hubble flow are receding from us at exactly the speed of light. It is calculated by the formula R sub h equals c over h. R sub h is the Hubble radius. C is the speed of light in vacuum, 299,792,458 meters per second exactly. H is the Hubble parameter at the present epoch. Plug in the Planck 2018 value of the Hubble constant, do the unit conversions, and the present Hubble radius comes out to about 14.5 billion light-years, or 1.37 times 10 to the 23 kilometers, or 8.53 times 10 to the 22 miles. A galaxy currently located at exactly the Hubble radius is receding from us at the speed of light right now. The cosmic event horizon is the boundary beyond which events occurring today can never send signals that will reach us, even given the entire infinite future of the universe to make the journey. The formula for the event horizon distance is d sub e of t naught equals c times the integral of dt over the scale factor a of t, evaluated from today out to infinity. D sub e is the event horizon distance. C is the speed of light. The scale factor a of t describes how the universe expands with cosmic time. The integral runs from today, t naught, into the infinite future. Plug in Lambda-CDM with the Planck 2018 parameters, and the event horizon comes out to about 16.7 billion light-years, or 1.58 times 10 to the 23rd kilometers, or 9.81 times 10 to the 22nd miles. Now look at what those three numbers, taken together, are saying. The particle horizon, 46.1 billion light-years, is the maximum distance from which we can currently observe light. The event horizon, 16.7 billion light-years, is the maximum distance from which any future signal can ever reach us. The difference between those two numbers is the difference between the universe we can see and the universe we can ever causally engage with. Roughly 95% by co-moving volume of the currently observable universe is already past the cosmic event horizon. We see those regions only because their light was emitted billions of years ago, when the geometry was different and the recession was slower. The galaxies whose photons are arriving in our telescopes tonight from beyond the event horizon are like letters from people who no longer have an address we can write back to. The conversation is permanently one way. It ends as soon as the last in-transit photon arrives. This is the prison. Not a wall in space, a boundary in space-time. A consequence of the geometry of an accelerating universe combined with the finite speed of light. Geraint Lewis, astrophysicist at the University of Sydney, and Pim van Oorschot, working with him on cosmological models, published an analysis showing that the Hubble sphere is not, in fact, a fundamental horizon at all. Light can cross it. In some cosmological models, light can cross it more than once. The Hubble sphere is a kinematic surface, a place where coordinate recession speed equals c. It is not where causality is severed. The actual severance happens at the event horizon, deeper in, harder to visualize, more disturbing because it cannot be photographed. What does it mean that the most important boundary in cosmology is one that cannot be drawn on any sky map, because it depends not only on where things are, but on how the universe is going to behave for the rest of time? Picture a coastline drawn on an old nautical chart. The cartographer can mark every visible feature, every island, every reef. What he cannot mark is the line beyond which a vessel, given infinite time and unlimited fuel, would still be unable to return to port because of currents that intensify with distance. The chart shows what is. The boundary in question describes what can ever be reached. It is not a feature you can see. It is a feature implied by the dynamics of the medium. The cosmic event horizon works the same way. The sky shows you objects. The horizon is implied by what the sky is doing. To understand how we arrived at the picture of an accelerating, eternally expanding universe, we have to walk through a sequence of observations and mathematical derivations that took roughly a century to assemble. The story begins with Albert Einstein. Between 1915 and 1917, working at the Prussian Academy of Sciences in Berlin, Einstein completed the field equations of general relativity. The equations describe how matter and energy curve space-time, and how that curvature, in turn, dictates the motion of matter and energy. When Einstein applied the equations to the universe as a whole, he ran into a problem. The equations did not allow for a static cosmos. Matter would gravitationally attract other matter, and the whole thing would collapse. Einstein, like virtually every astronomer of his era, believed the universe was static. So, he inserted a term into the equations to hold it in place. He called it the cosmological constant. He gave it the symbol capital Lambda. He balanced its value precisely so that the gravitational tendency to collapse would be cancelled by a uniform repulsive contribution everywhere in space. It was a fudge. Einstein knew it was a fudge, but it preserved the static universe. In the 1920s, two developments dismantled the static picture. Vesto Slipher, working at the Lowell Observatory in Arizona, measured the redshifts of light from distant nebulae, the objects we now call galaxies. The vast majority of them were redshifted, meaning their light was stretched toward longer wavelengths, consistent with motion away from the observer. In 1927, the Belgian physicist and Catholic priest Georges Lemaître, working at the Catholic University of Louvain, derived from Einstein's own equations that the universe must be expanding. Lemaître's paper, published in French in an obscure Belgian journal, was largely ignored for several years. In 1929, Edwin Hubble, working at Mount Wilson Observatory in California, published a paper showing that the recession velocity of galaxies was proportional to their distance. That relationship, the Hubble-Lemaître law, has the simple mathematical form V equals h naught d. V is recession velocity, h naught is the Hubble constant, the present expansion rate, d is the proper distance to the galaxy. More distant galaxies recede faster, with the relationship being linear at moderate distances. Einstein, when shown the evidence, withdrew his cosmological constant. He reportedly called it his greatest blunder. The story is colourful, but in fairness, the historical record is more nuanced. Whether Einstein used those exact words is debated by historians of science. What is not debated is that, by the late 1920s, the static universe picture was dead. The expansion was real, and Einstein no longer needed lambda to make the equations match observations. For the next 70 years, the cosmological constant was treated as a curiosity. Physicists assumed it was zero. The universe was expanding, and the expansion was decelerating, slowing down under the gravitational pull of all the matter contained within it. The only question was whether the matter density was high enough to eventually halt and reverse the expansion, leading to a big crunch, or whether the universe would expand forever, gradually cooling and thinning toward heat death. Then came 1998. Two independent teams of astronomers, the Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University and Adam Rees at the Space Telescope Science Institute, were measuring the expansion history of the universe by observing Type 1a supernovae, the thermonuclear detonations of white dwarf stars. Type 1a supernovae have a roughly standard intrinsic brightness, which means their apparent brightness can be used to infer their distance. By comparing distances to redshifts, the teams could reconstruct the expansion history of the cosmos. The result, when it came in, was not what either team expected. The expansion was not slowing down, it was speeding up. The most distant supernovae were dimmer than they should have been if the universe had been decelerating. They appeared to be farther away than the matter content alone could explain. Cosmic acceleration was real. The mathematical interpretation required reviving Einstein's cosmological constant, but with a positive value, large enough to overcome the gravitational deceleration of all the matter in the universe and produce net acceleration. Or, equivalently, the universe was filled with some new form of energy, dubbed dark energy, that exerted negative pressure and drove space apart. Whatever it was, it had to constitute roughly 70% of the total energy budget. It had to be smooth, present everywhere, with no detectable clumping. And, critically, it had to be associated with the structure of space itself, because its density appeared to remain roughly constant even as space expanded, which is the opposite of what ordinary matter and radiation do. Perlmutter, Schmidt and Rees shared the 2011 Nobel Prize in Physics for the discovery. The discovery was real. The cause of the acceleration was, and remains, unidentified. This brings us to the second foreshadowing point of this exploration. The dominant component of the universe, the term that is going to drive the formation of the cosmic event horizon and lock every future observer inside an island universe, is a component whose physical nature science cannot currently explain. It is not a particle that has been detected. It is not a field that has been characterized. It is a number in an equation, a value that fits the data, an effect whose source remains obscure. We will return to this when we examine what the equations are actually telling us and what they are not. The Friedmann equations, derived in the 1920s by the Russian mathematician Alexander Friedmann from Einstein's field equations, describe how the scale factor of the universe evolves over cosmic time. The scale factor, denoted A of t, measures how distances between unbound objects change as the universe expands. The first Friedmann equation, in its full form, is this. Open parenthesis, A dot over A, close parenthesis, squared, equals 8 pi g over 3 times rho minus kc squared over a squared plus capital lambda c squared over 3. A dot over A is the rate of change of the scale factor relative to the scale factor itself, which is the Hubble parameter at any given epoch. G is Newton's gravitational constant. Rho is the total energy density of the universe. K is the spatial curvature parameter. Lambda is the cosmological constant. C is the speed of light. The equation describes how expansion is driven by total energy density, modified by curvature, and modified again by the cosmological constant. The corresponding acceleration equation, which captures the second derivative of the scale factor, is this: A double dot over A equals minus 4 pi g over 3 times, open parenthesis, rho plus 3p over c squared, close parenthesis, plus lambda c squared over 3. The new variable is p, the pressure of whatever fills the universe. For ordinary matter, the first term dominates and is negative, meaning expansion decelerates. For dark energy, with its highly negative pressure, the first term flips sign, and combined with the lambda term, expansion accelerates. These equations are not speculative. They are derived rigorously from the field equations of general relativity, and they have been tested against observations across an enormous dynamic range. Big Bang nucleosynthesis calculations, performed using these equations, predict the abundances of light elements, hydrogen, helium, lithium, formed in the first 3 minutes of the universe. Those predicted abundances match observed primordial abundances to remarkable precision. The cosmic microwave background, predicted by George Gamow and his collaborators in the 1940s as a relic of the hot early universe, was discovered in 1965 by Arno Penzias and Robert Wilson at Bell Labs, who initially thought the persistent microwave hiss in their horn antenna was caused by pigeon droppings. They cleaned the antenna. The signal remained. The signal was, as they soon learned, the afterglow of the Big Bang, a sea of microwave photons cooled by cosmic expansion to a temperature of about 2.7 Kelvin. The discovery earned them the 1978 Nobel Prize in Physics. The CMB has been mapped with progressively higher precision by 3 NASA and ESA missions. NASA's Cosmic Background Explorer, COBE, launched on November 18, 1989, weighed about 5,000 pounds, measured 16 feet long and 28 feet across with its solar panels deployed, and drew about 712 watts of power. COBE's FIRAS instrument confirmed that the CMB has the spectrum of a blackbody to extraordinary precision, the most perfect blackbody spectrum ever measured in nature. COBE's DMR instrument detected the first temperature anisotropies, the tiny variations in CMB temperature that correspond to density variations in the early universe, and the seeds from which galaxies later formed. NASA's Wilkinson Microwave Anisotropy Probe, WMAP, launched on June 30, 2001, mapped those anisotropies at higher resolution, determining the age of the universe to within about 0.5%, and the geometry of space to be flat to within about 0.4%. The European Space Agency's Planck spacecraft, launched on May 14, 2009, with a 1.5-meter primary mirror and instruments spanning frequencies from 30 to 857 gigahertz, brought CMB precision close to the fundamental astrophysical limit. What COBE, WMAP, and Planck collectively established is that the temperature of the CMB at the present cosmic epoch is 2.7255 Kelvin. The CMB was emitted approximately 370,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen, releasing the photons that had been trapped in the dense plasma. Those photons have been traveling ever since, redshifting as space expanded. The CMB is the most distant light any telescope can ever observe, in principle. It marks the wall of the observable universe, the surface of last scattering, the moment before which the universe was opaque. The CMB is one of the firmest pillars of the Big Bang model. Without the CMB, the hot early universe would be theoretical inference. With the CMB, it is a measured fact. This is the third foreshadowing point. The CMB, central pillar of empirical cosmology, is presented in textbooks as a permanent feature of any sky observed by any future astronomer. We will return to that assumption. Keep this in mind. The pillar is more fragile than the textbooks suggest, and the geometry of cosmic expansion has consequences for what observable evidence can persist over deep time. Lambda-CDM, with its accelerating expansion, has a future. The future is called the de Sitter limit. Willem de Sitter, the Dutch astronomer who corresponded with Einstein in the 1910s and 1920s, derived a solution to the Einstein field equations, describing an empty universe with a positive cosmological constant. In de Sitter's solution, space expands exponentially forever. Distances between any 2 points double over a fixed time interval, then double again, then double again. The expansion rate in the de Sitter limit becomes constant, with the Hubble parameter approaching a fixed asymptotic value determined entirely by the cosmological constant. If Lambda-CDM is correct, and if lambda is truly constant, then in the very far future, after all the matter has been diluted by expansion to negligible density, the universe approaches a de Sitter state, empty, exponentially expanding, with a permanent cosmic event horizon. In 1977, Stephen Hawking and Gary Gibbons published a paper analyzing the thermodynamics of cosmological event horizons. What they found was that just as black hole horizons have an associated temperature, the Hawking temperature, cosmological horizons also have an associated temperature. The formula is T equals h bar h over 2 pi k sub b. T is the horizon temperature. H bar is the reduced Planck constant, h divided by 2 pi. H is the Hubble parameter. K sub b is Boltzmann's constant. Plug in the Lambda-CDM parameters at the de Sitter asymptote, and the temperature comes out to roughly 10 to the minus 30 Kelvin. Unimaginably cold, but not zero. Gibbons and Hawking also found that the horizon has an associated entropy, given by S equals A over 4G in natural units, where A is the area of the horizon and G is Newton's gravitational constant. The cosmological event horizon has an entropy. It carries information, or rather, it bounds information. The area of the horizon measures, in some sense, the maximum amount of information that can ever be received by an observer at its center. The prism is not just causal, it is informational. It is thermodynamic. It is woven into the deepest structure of physics. What does it mean that the universe, in the mainstream cosmological picture, ends not in fire and not in ice, but in an ever-emptying stage where every observer sits at the center of a finite information sphere with a temperature 1 trillion times colder than empty interstellar space. Take a moment to sit with that. There is no rush. The implications are larger than the equations. Now we have to confront the work of Lawrence Krauss and Robert Scherrer in detail, because their 2007 paper is the conceptual keystone of this entire exploration. The paper, titled "The Return of a Static Universe and the End of Cosmology," appeared in 2007 in the journal General Relativity and Gravitation, and a longer version was published in 2008 in the International Journal of Modern Physics D. Krauss is a theoretical physicist who has held positions at Yale, Case Western Reserve, and Arizona State. Scherrer is a cosmologist at Vanderbilt University. Both are mainstream researchers, working within Lambda-CDM, accepting the standard parameters, deriving consequences from the standard equations. The question Krauss and Scherrer asked was this: if the present cosmological model is correct, what will the universe look like to intelligent observers in the very far future, billions to trillions of years from now? They worked through the calculation systematically. They considered the redshift of external galaxies. They considered the cosmic microwave background. They considered the abundances of primordial light elements. They considered the local large-scale structure, each in turn. The conclusion was the same in every case. The evidence dies. External galaxies, redshifted by ongoing cosmic expansion, will eventually be redshifted to infinity. Krauss and Scherrer estimated, drawing on calculations by Krauss and Glenn Starkman of Case Western Reserve, that by 100 billion years from now, the redshift of all galaxies external to the local group will exceed 5,000. By 10 trillion years, the redshift will reach approximately 10 to the 53rd. The light from those galaxies, originally optical or ultraviolet, will be stretched into wavelengths longer than the entire diameter of the observable universe. The light will not have ceased to exist. It will have been stretched out of any conceivable detector. The cosmic microwave background suffers a different fate. Krauss and Scherrer calculated that when the universe is roughly 25 times its present age, the CMB will be redshifted to wavelengths longer than about 300 kilometers, or 186 miles, corresponding to frequencies below approximately 1 kilohertz. This is below the plasma frequency of the ionized interstellar medium of any galaxy. The plasma frequency, denoted nu sub p, is given by the formula nu sub p equals the square root of n sub e times e squared over pi times m sub e. N sub e is the electron density. E is the electron charge. M sub e is the electron mass. Below the plasma frequency, electromagnetic waves cannot propagate through an ionized medium. They are reflected or absorbed. They cannot be received from outside. This means that even if the CMB still exists physically, observers inside any galaxy surrounded by interstellar plasma will not be able to detect it. The galaxy itself becomes a screen. The Big Bang afterglow, the most decisive empirical evidence for the hot early universe, is hidden by local plasma physics. It is still real. It is still there. It is unobservable. Primordial nucleosynthesis suffers a third kind of erasure. The primordial abundances of hydrogen, helium, and lithium are inferred today by measuring those abundances in old, low metallicity stars and gas clouds, where stellar processing has not yet contaminated the original ratios. Over deep time, every gas cloud in the local supergalactic remnant will be processed and reprocessed by successive generations of stars. The original primordial abundances will be overwritten by stellar nucleosynthesis. Future astronomers, looking at the chemical composition of stars in their galaxy, will see only the integrated history of stellar processing, with no clean primordial record to compare against. Three pillars of the Big Bang model, three independent erasures, all converging on the same conclusion. By somewhere between 100 billion and 10 trillion years from now, the empirical case for cosmological expansion, for a hot, early universe, for any of the structure that supports the modern picture of cosmology, will have evaporated from view. Krauss and Scherrer's exact phrase in the 2008 paper deserves to be quoted carefully. They wrote that future observers will be fundamentally incapable of recovering the true large-scale history of the universe. Not unaware, not poorly equipped, fundamentally incapable. The data needed for the inference will not exist in any accessible form. Abraham Loeb, Frank B. Baird, Junior Professor of Science at Harvard, working with Kentaro Nagamine of the University of Nevada, Las Vegas, simulated the future evolution of large-scale structure in a Lambda-CDM universe. Their simulations found that the local group, the gravitationally bound system containing the Milky Way, Andromeda, the Triangulum galaxy, and dozens of smaller satellite galaxies, will eventually consolidate into a single merged galaxy. The Milky Way and Andromeda are already on a collision course, expected to begin merging in roughly 4 billion years. Once the merger completes, the resulting elliptical galaxy, sometimes called Milkomeda in popular treatments, will sit alone in the local volume. All other galaxies will have receded beyond the cosmic event horizon. The visible cosmos, from the perspective of any observer inside Milkomeda, will consist of one galaxy surrounded by silence. What does it mean that the cosmos, currently teeming with hundreds of billions of galaxies, will eventually present itself to its inhabitants as a single isolated island in an empty void? Picture an old town surrounded by neighboring villages, each connected by a network of roads. Every road, over the course of years, slowly stretches. The villages do not move on their own. The land between them grows. The roads, originally short, become longer. After enough centuries, the journey between any two settlements takes longer than a human lifetime. After enough millennia, the roads have stretched beyond the range of any practical travel. The villages are still there. The townspeople do not know it. They have lost contact. They have lost evidence that there was ever anything outside their walls. A historian in the town, working with whatever records remain, may eventually conclude that the town was always alone, that the stories of other villages were folklore, that the world ends at the visible horizon. The historian will be wrong. The historian will be honest. The historian will have no way to discover the truth. This is the Krauss and Scherrer scenario, made small enough to hold in the mind. Now we have to address something subtle but important. Our present epoch is not a typical epoch. We sit at a moment in cosmic history when most of the universe is still visible, when the CMB is still detectable, when galaxies have not yet receded out of contact, when the empirical case for cosmology can still be made. This window is not eternal. It is closing. Krauss and Scherrer made the point explicitly. They argued that we may live in one of the few epochs in which the universe can be correctly inferred from observation. Earlier, before the CMB was bright enough, or before galaxies had formed, the data were not yet available. Later, the data will be gone. In between, there is a window. We are in it. The window is real. The window has a beginning and an end. What does it mean that the period of cosmic history during which intelligent observers can correctly understand the cosmos is finite? This is the fourth foreshadowing point. We will return to this when we examine what materialism actually predicts about the relationship between observability and reality. The observation that observability is temporary has implications. We will not draw those implications yet. We will note that they exist. The mainstream model, Lambda-CDM, is wildly successful at fitting current observational data. It is also incomplete. The two largest open problems in modern cosmology, both of which directly bear on the future of the cosmic prison, are the cosmological constant problem and the Hubble tension. We will examine each carefully, because they are both points where the model fits the data without explaining the data, and they are both points where the standard interpretation has had to be repeatedly adjusted to accommodate new measurements. Stephen Weinberg, the late theoretical physicist who won the 1979 Nobel Prize in Physics for his work on electroweak unification, devoted considerable attention to the cosmological constant problem in the 1980s and 1990s. Weinberg formulated what he called the old and new cosmological constant problems. The old problem is this. Quantum field theory predicts that the vacuum, empty space, has a certain energy density. When physicists calculate this vacuum energy from first principles, the result depends on the highest energy scale at which quantum field theory is valid. If that scale is the Planck energy, the natural ultraviolet cutoff in quantum gravity, the predicted vacuum energy density is enormous, roughly 10 to the 120 times larger than the observed dark energy density. This is the largest discrepancy between theoretical prediction and observation in the history of physics, by many orders of magnitude. It has been called, with some justice, the worst prediction in science. The new cosmological constant problem, formulated by Weinberg in 2000, is more subtle. It asks why the observed vacuum energy density, even though it is vastly smaller than the naive theoretical prediction, happens to be of the same order of magnitude as the present mass density of the universe. The two quantities, vacuum energy density and matter density, evolve differently with cosmic expansion. Matter density falls as the cube of the scale factor. Vacuum energy density, if lambda is truly constant, remains constant. The fact that they are comparable today, when through almost all of cosmic history they were not comparable, is a coincidence of timing. The timing is unexplained. Our presence inside that narrow overlap is unexplained. Weinberg's two problems are not loose ends. They are central incompletions. The dominant component of the universe, the term that drives the cosmic event horizon, the parameter that determines the entire structure of the late-time prism, is a parameter whose theoretical value is wrong by 120 orders of magnitude, and whose observed value is, against all expectation, of the same order as the present matter density. The mathematical model accommodates these facts. The mathematical model does not explain them. Sean Carroll, theoretical physicist at Johns Hopkins University, has written extensively on the cosmological constant. His position, summarized in multiple review articles, is that lambda is a small but potentially non-zero vacuum energy whose observational success in fitting late-time expansion has to be balanced against its theoretical awkwardness. Mainstream cosmologists do not pretend the problem is solved. They work around it, using the observed value as input to the model and computing consequences. The Hubble tension is the second great open problem. The Hubble constant, h0, the present rate of cosmic expansion, can be measured in two independent ways. The first is the local distance ladder, which uses Cepheid variable stars and Type 1a supernovae in nearby galaxies to derive a value directly. This is the method pioneered by Edwin Hubble in 1929 and refined by generations of astronomers since. The current local distance ladder value, as of the 2026 H0DN consensus paper from a coalition of cosmology groups, is 73.50 plus or minus 0.81 kilometers per second per megaparsec. The second method is to measure H0 indirectly by fitting Lambda-CDM to the cosmic microwave background and projecting the inferred parameters forward to the present epoch. This is the method used by the Planck collaboration. The Planck-derived value is 67.4 plus or minus 0.5 kilometers per second per megaparsec. The H0DN paper compares this value to the local consensus and finds a 7.1 sigma discrepancy in their joint analysis with Planck, the South Pole Telescope, and the Atacama Cosmology Telescope. NASA's Hubble Space Telescope materials, updated in 2025, state the situation directly. They say, "Today, the Hubble tension is still a mystery. Two methods, two values. They disagree by about 9%. Neither has identifiable errors that would explain the discrepancy. The implications, if the tension is real, are profound. Either there is something wrong with our understanding of the early universe, the late universe, or both. Either the standard model has new physics hiding in it, or the measurements are systematically biased in ways no one has yet identified." Adam Rees, one of the original discoverers of cosmic acceleration and a major figure in distance ladder cosmology, has argued repeatedly that the local measurements are robust. The Planck team has argued repeatedly that their CMB measurements are robust. Both teams are right that their methods, taken individually, are sound. The contradiction lives in the comparison between them. This is the fifth foreshadowing point. We will return to it. The mainstream model, the framework on which the entire prison architecture rests, is currently in tension with itself. Two ways of measuring the same parameter give different answers. The model has not been adjusted to resolve the tension. The tension is acknowledged and the work continues. The Dark Energy Spectroscopic Instrument, DESI, located at the Mayall Telescope on Kitt Peak in Arizona, is currently the most ambitious instrument ever built to characterize dark energy directly. DESI began its main survey in May 2021. It uses 5,000 robotic fiber positioners, each capable of aligning to within 10 microns, feeding 10 spectrographs that record galaxy redshifts at high precision. DESI's measurements employ baryon acoustic oscillations, the imprint of pre-recombination sound waves in the matter distribution, which serve as a standard ruler for cosmic geometry. These baryon acoustic oscillations act as frozen sound waves from the early universe, providing precise distance measurements that complement CMB and supernova data. DESI's first-year data release in 2024 included over 6 million extragalactic objects across redshifts from 0.1 to 4.2. When DESI BAO measurements were combined with Big Bang nucleosynthesis priors and the CMB acoustic scale, the derived Hubble constant was 68.52 plus or minus 0.62 kilometers per second per megaparsec. In some combinations of DESI BAO with CMB and supernova data, the analysis showed mild preferences for a time-varying dark energy equation of state instead of a strict cosmological constant. The hint was not a discovery, it was a hint. Berkeley Lab announced in April 2026 that DESI had completed its originally planned 5-year three-dimensional map of the universe, cataloguing more than 47 million galaxies and quasars, plus more than 20 million stars. Berkeley Lab's 2026 summary noted that dark energy might be evolving over time, while emphasizing that the hints remain under study and could either disappear or strengthen as the full analysis matures. The European Space Agency's Euclid mission, launched in July 2023 and beginning routine science observations in February 2024, complements DESI from space. Euclid is mapping billions of galaxies across more than a third of the sky, out to distances of about 10 billion light-years, probing dark energy and dark matter through 3 independent methods: weak gravitational lensing, galaxy clustering, and the geometry of large-scale structure. Euclid's Deep Field Preview data, released in 2024, contained 26 million galaxies in just 1 week of deep observations, with the most distant detected beyond 10.5 billion light-years. These are not small instruments. These are not preliminary efforts. They are collectively the largest investment in observational cosmology in human history. The situation they have produced is this. The standard model, Lambda-CDM, fits the data well enough to describe the prison. The standard model does not yet explain the dominant component of the data. Dark energy, the substance that drives the event horizon, remains physically unidentified. Whether it is a true cosmological constant or a slowly evolving field is, as of this exploration's recording, an open question. Picture a marine biologist who has spent her career studying a single lagoon. She has identified every species, mapped every current, characterized every chemical constituent. She knows the lagoon thoroughly. Then someone tells her that the lagoon connects, through narrow channels, to an ocean that runs for thousands of miles in every direction. The ocean's chemistry, she is told, may differ from the lagoon's in ways her instruments have not measured. Everything she discovered about the lagoon remains true. None of it describes the ocean. The lagoon is real. The lagoon is well characterized. The lagoon is not the whole picture. This is the situation modern cosmology occupies. The model fits the lagoon. We do not yet know what the ocean is doing. What does it mean that the most precise measurements of the cosmos in human history have, simultaneously, sharpened our description of the prison and deepened our ignorance about what builds it? Stay with that question. The implications run further than they first appear. In a Lambda-CDM universe with a true cosmological constant, the late-time behavior is determined by lambda alone. The matter density falls towards zero. The radiation density falls even faster. The cosmological constant, by definition, remains constant. As cosmic time advances, the dynamics approach the de Sitter limit. The Hubble parameter approaches a fixed asymptote. The expansion becomes purely exponential. Distances between unbound objects double over a fixed timescale, then double again, then double again. Anything not gravitationally bound at the time of crossover gets carried away by the expansion, redshifted to silence, removed from causal contact. Within a few Hubble times, in cosmic terms, the universe outside the local supergalaxy becomes dark and empty. This is the future Krauss and Scherrer were extrapolating. This is the future every Lambda-CDM cosmologist who has run the equations forward has obtained. There is no controversy about the result, conditional on the model being correct. The conditionals are doing significant work. If the cosmological constant is truly constant, the future is de Sitter. If dark energy evolves, the future could differ. If it evolves toward more negative effective pressure, with equation of state parameter W less than -1, the universe could undergo what Robert Caldwell and others have called a big rip, in which the accelerating expansion grows. So violent that it tears apart galaxies, then solar systems, then planets, then atoms, in a finite time. Lewis and Van Oorschot used phantom energy cases specifically to demonstrate that in such cosmologies, the Hubble sphere is not a fundamental horizon because light can cross it more than once. The phantom case illustrates that the geometry of the prison, in detail, depends on the nature of dark energy. If, alternatively, dark energy weakens over time, the future could be different again. Quintessence models, in which dark energy is a slowly evolving scalar field, allow for a wide range of late-time behaviors, depending on the field's potential. Some quintessence trajectories asymptote to de Sitter, some asymptote to flat space, some asymptote to recollapse. The DESI hints of evolving dark energy, if they survive further analysis, would push us toward a quintessence-like picture. The hints are not yet confirmation, they are hints. Modified gravity offers a third class of alternatives. Instead of attributing acceleration to a new substance, modified gravity theories attribute it to a breakdown of general relativity on cosmological scales. Joshua Freeman of the University of Chicago, Michael Turner of Kavli Institute for Cosmological Physics, and Dragan Hutera of the University of Michigan, in a major review of dark energy, explicitly noted that cosmic acceleration could reflect either a new energy component or a failure of general relativity at large scales. Recent growth of structure tests, including measurements reported in coordination with DESI in 2026, have continued to support Einstein gravity over most of cosmic history, narrowing the room for some modified gravity options without eliminating them. The story is open. The mainstream picture, eternally accelerating Lambda-CDM, remains the leading hypothesis. It is not the only hypothesis. What does it mean that the very feature determining the eternal architecture of the prison is the feature physics has most failed to explain? The Lambda-CDM picture, even at its most successful, is a description of mechanism, not a description of origin. The Friedmann equations describe how a universe with given energy content evolves. The equations do not describe why the universe contains those energy contents. The equations do not describe why lambda has a positive value rather than 0 or negative. The equations do not describe why the initial conditions at the Big Bang were what they were. These questions are not failures of the model. They are outside the model. The model is a calculation engine for processing initial conditions and energy contents into observable predictions. It is not a metaphysical answer. The acceleration discovery in 1998 was not the first time physics had encountered a phenomenon whose mechanism was clear and whose source was hidden. The discovery of dark matter in the 1930s by Fritz Zwicky, studying the Coma cluster, had a similar character. Zwicky observed that galaxies in the cluster were moving too fast to be held together by the gravity of their visible matter alone. He postulated dark matter, unseen mass, to make the dynamics work. The mainstream took decades to accept his conclusion. Today, dark matter is part of the standard cosmological model. Today, dark matter has not been directly detected, despite decades of underground experiments, particle accelerators, and astronomical surveys. The mass is real. The substance is unidentified. Cosmology has, in fact, two major dark components: dark matter and dark energy, totaling roughly 95% of the energy budget. Both are inferred. Both are unidentified. The empirical case is overwhelming. The theoretical understanding is partial. This is what science looks like at the frontier. It is not what science looks like in the popular imagination. The popular imagination treats science as a sequence of decisive answers, each replacing the last in a march toward total understanding. The actual practice is different. The actual practice is a sequence of increasingly precise descriptions, each of which raises new questions, some of which remain unanswered for decades or centuries. The Hubble tension, if it persists, will join the cosmological constant problem as a permanent monument to mainstream cosmology's incompletion. Now we move to the deeper question. We have been describing a prison whose existence the equations of Lambda-CDM fitted to current data predict. The prison is a real consequence of the model, given the parameters. The model does not explain the parameters. The model does not explain why lambda has the value it has. The model does not explain why the universe began in a hot, dense, highly ordered state with low entropy and exquisite fine-tuning of constants. The model does not explain why there is a model at all, why mathematical regularities apply to physical reality, why the cosmos is intelligible to creatures whose minds, on any naturalistic account, were shaped to track prey across savannas, rather than to comprehend the structure of space-time. Earlier in this exploration, we noted that the dominant component of the universe is physically unexplained. Earlier, we noted that the empirical evidence for cosmology has a finite observational lifetime. Earlier, we noted that future observers will be fundamentally incapable of recovering the true history of the cosmos. Earlier, we noted that the Hubble tension represents a 7.1 sigma discrepancy between two equally legitimate measurement methods, with no resolution. We said, in each case, that we would return. We are returning now. Some commentators, looking at the cosmic event horizon and the immense scale of the observable universe, draw a particular conclusion. The conclusion is presented as if it followed naturally from the physics. It is presented in popular books, in television documentaries, in widely circulated essays. The conclusion is this: cosmic vastness, combined with the eventual causal isolation of every observer, implies that human life is insignificant, that the universe is purposeless, and that any intuitions of meaning or design are projections of psychology onto a fundamentally indifferent cosmos. Let us examine this claim carefully, in its strongest form, before testing whether it survives scrutiny. The argument runs as follows. Earth is one planet around an unremarkable star, in an unremarkable galaxy, in a cosmos containing hundreds of billions of galaxies. The total volume of the observable universe is approximately 10 to the 80th cubic meters. The total mass is roughly 10 to the 53rd kilograms. The age of the universe is roughly 10 to the 17th seconds. Human civilization, in the grand sweep, is a momentary flicker on a tiny rock. Worse, the cosmic event horizon means that everything beyond about 16.7 billion light-years is causally severed from us. We cannot influence those regions. We cannot communicate with those regions. We cannot, in any meaningful sense, matter to them. The universe is enormous, indifferent, and most of it is already beyond our reach. Therefore, the argument concludes, the cosmos has no purpose, human existence has no inherent meaning, and any feelings to the contrary are psychological projections produced by the mind itself. That is the argument in its most coherent form. Now let us test it. The argument depends on a hidden premise. The premise is that significance correlates with physical magnitude. That if you are physically small, you are metaphysically insignificant. That if you cannot causally affect a region of space, that region's existence reduces your meaning. State the premise explicitly, and it begins to look strange. We do not, in any other context, believe that significance scales with size. A diamond is significant despite being smaller than a pebble. A child's life is significant despite being smaller than a stadium. A library's contents are significant despite weighing less than the building that houses them. The relationship between physical magnitude and meaning is not one we accept anywhere except somehow in cosmology, where we are suddenly told that vastness implies meaninglessness. The premise is doing all the philosophical work, and the premise is unsupported. It does not follow from any equation. It is a sentiment imported into the physics, dressed up as if it followed from the data, and then attributed to the data. This is not science. It is editorial commentary disguised as science. Worse, the argument contains an internal contradiction. If physical magnitude determines meaning, and the universe is vast, then the universe is what is significant, not the observers within it. By the argument's own logic, cosmic vastness should imply that the cosmos itself is enormously significant. But the argument concludes the opposite, that the cosmos is indifferent and meaningless. To get from cosmic vastness to cosmic meaninglessness, the argument has to swap premises in midstream. It has to assert that vastness implies significance for the vast object only, and meaninglessness for the small observer. This is not logic. This is a non sequitur. Picture a librarian working in a vast library. Imagine a critic walking in and saying, "The library contains millions of books, therefore your work is meaningless." The librarian, presumably, would point out that the existence of many books does not diminish the value of the one she is currently cataloguing. The premise that scale destroys meaning is not a premise anyone accepts in ordinary reasoning. It is invoked in cosmology specifically because, in cosmology, the scales are large enough to feel intuitive. Intuition is not an argument. The intuition collapses on examination. Now consider the second claim, the one we have been foreshadowing for over an hour. The claim is that because physics describes cosmic acceleration and the formation of the event horizon, no creator is needed to explain the universe. The Friedman equations work. The CMB matches predictions. The supernovae trace the expansion history. The standard model fits the data. Therefore, the argument runs, the cosmos is self-explanatory, and any further questions about origin or design are unscientific. Examine this carefully. Examine what the equations actually do. The Friedman equations describe how a universe evolves given certain energy contents, certain initial conditions, and certain values of fundamental constants, including the cosmological constant. The equations do not derive the energy contents. They take energy contents as input. The equations do not derive the initial conditions. They take initial conditions as input. The equations do not derive lambda. They take lambda as input. A description of a process is not an explanation of why the process exists. A description of a mechanism is not an account of why the mechanism is in operation. The Friedman equations are spectacular at their job. Their job is to compute consequences. Their job is not to explain why they have something to compute consequences from. The cosmological constant problem is the sharpest illustration. Quantum field theory, our best description of microphysics, predicts a vacuum energy density some 120 orders of magnitude larger than the value we observe. The discrepancy is acknowledged by every working theoretical physicist. The discrepancy means that the universe behaves as if lambda were extraordinarily small, while the underlying physics on its own predicts lambda to be extraordinarily large. The two are reconciled by, in effect, fine-tuning. The bare value of lambda from quantum gravity, whatever it is, must be cancelled by some other contribution to within 1 part in 10 to the 120. This is precision beyond any precision in any other measurement in physics, by many, many orders of magnitude. When a theory's most basic prediction is wrong by 120 orders of magnitude, and the universe's actual behavior agrees with the alternative value to that same precision, you are not looking at a triumph of self-explanation. You are looking at an unexplained parameter whose value happens to be set, against all theoretical expectation, to exactly what is required for the existence of stars, galaxies, planets, and observers. That is the fine-tuning argument, applied to the cosmological constant specifically. Luke Barnes, astrophysicist at Western Sydney University, has reviewed the scientific literature on cosmic fine-tuning extensively. His treatment is careful. He does not overclaim. He notes that not every claim of fine-tuning in popular literature holds up. Fred Adams, astrophysicist at the University of Michigan, has shown in detailed calculations that some parameter ranges associated with stellar viability are actually broader than once supposed. The fine-tuning case has to be made carefully, with attention to which parameters are genuinely constrained and to what degree. But Barnes's overall conclusion, after engaging seriously with both fine-tuning advocates and skeptics, is that the cosmological constant remains one of the strongest examples. Whatever cancels the bare quantum gravitational vacuum energy down to its observed value is a feature of nature whose cosmic scale precision is, on any honest accounting, extraordinary. What does it mean that the most successful description of the universe in human history is built on a parameter whose theoretical prediction is wrong by 10 to the 120th, and whose actual value lies precisely in the narrow range that allows a structured cosmos to exist? The materialist response to this situation is well documented. The response is the multiverse. We will examine it now. Some cosmologists, faced with the apparent precision of lambda, propose that there exist a vast or infinite ensemble of universes, each with different values of the cosmological constant. Most of those universes in this proposal are inhospitable, with values of lambda too large or with the wrong sign. A small subset have values like ours, hospitable to structure formation. We naturally find ourselves in a hospitable universe, because we could not exist in a hostile one. The apparent fine-tuning on this account is not real. It is a selection effect. The multiverse proposal deserves a fair hearing. Steven Weinberg himself, in his work on the cosmological constant, noted that anthropic reasoning combined with a multiverse could, in principle, address the cosmological constant problem. Weinberg presented it as a possibility, not a settled solution. Many cosmologists since have explored similar lines. The proposal has genuine technical content, deriving in some versions from inflationary cosmology, and in others from string-theoretic landscape considerations. Now examine the proposal critically. Several problems emerge. First, the multiverse has no observational evidence. No other universe has been detected. By construction, no other universe can be detected, since the proposal is that the other universes are causally disconnected from ours. The proposal is therefore unfalsifiable. There is no possible observation that could distinguish between a universe in which the multiverse exists and a universe in which it does not. By the standards of empirical science, an unfalsifiable proposal is not a scientific hypothesis. It is a metaphysical hypothesis. A respectable one, perhaps, but not science. Second, the multiverse does not eliminate the explanatory question. It moves it. If there is a multiverse generating universes with various values of lambda, the multiverse-generating mechanism itself requires explanation. The questions multiply. The existence of the multiverse remains unexplained. The specific distribution of parameters it produces remains unexplained. The reason it produces any universes at all, rather than none, remains unexplained. The fundamental question, why is there something rather than nothing? Why is the something configured to permit observers? Has not been answered. It has been pushed up one level. The original problem reappears in the deeper layer. Third, the multiverse appeal is, by its own logic, an admission that the observed value of lambda is so improbable that ordinary chance cannot account for it. The motivation for invoking a multiverse is that the observed precision is too extraordinary to be coincidence in a single universe. The implicit acknowledgement, embedded in the multiverse proposal itself, is that fine-tuning is real and demanding of explanation. The multiverse advocate has already conceded the most important point. The disagreement is then about what kind of explanation is acceptable. An undetectable infinite ensemble of universes or an intelligent cause. Of those two options, only one matches what we already know about how parameter precision arises in our experience. When we encounter precise configurations elsewhere, in technology, in literature, in mathematics, in any human experience analog, the source is always intelligent decision. Combination locks do not set themselves. Symphonies do not compose themselves. Encryption keys do not generate themselves out of ambient noise. Picture a combination lock with 26 dials, each running from 0 to 1 trillion. The lock opens only when all 26 are set to specific values. Not approximately, exactly. The probability of finding the right combination by random rotation is a number small enough that it has no intuitive comparison. Here is the strange part. The dials were not set by anyone turning them. They appear to have come preset from the beginning. When you encounter such a lock, the inference to a setter is not strained. It is the obvious inference. The strained inference is to say, An infinite array of locks exists, and we happen to have stumbled into the one that was already open. The cosmological constant is the lock. The dials are preset. The inference to a setter is the simpler explanation. The multiverse is the contortion required to avoid that inference. What does it mean that the proposed alternative to design is an unfalsifiable, undetectable, infinite ensemble of universes whose generating mechanism requires its own explanation? Even some of the most prominent skeptics in the history of science have conceded the strangeness of cosmic precision. Sir Fred Hoyle, the British astronomer who coined the term Big Bang, who spent much of his career resisting Big Bang cosmology, who was, throughout his life, an avowed non-theist, made the calculation for himself. After working through the energy-level coincidences that allow carbon to form in stellar interiors, Hoyle wrote that a common-sense interpretation of the facts suggests that a super-intellect has monkeyed with physics, as well as with chemistry and biology, and that there are no blind forces worth speaking about in nature. Hoyle was no friend of theism. He had no rhetorical interest in supporting religious cosmology. He looked at the numbers and said what he saw. The fine-tuning of carbon was the precision he could test in the laboratory. The fine-tuning of lambda is more extreme by many orders of magnitude. If the carbon precision moved Hoyle, the lambda precision should move us. Picture a forensic accountant auditing the books of a corporation. The accountant has no interest in the outcome. He has no relationship with the employees. He tracks the numbers. Most discrepancies turn out, on examination, to be ordinary mistakes, transcription errors, miscategorized expenses, fixable problems. Suppose the accountant finds that one specific entry, the one that determines whether the company can operate at all, has been adjusted to within 1 part in 10 to the 120th against the expected baseline. He runs the calculation again. The result is the same. Each ordinary mistake explanation requires the entry to differ from the baseline by some plausible amount. None of them produce the observed precision. At a certain point, the accountant stops looking for clerical errors. He starts looking for a setter, someone who knew what value the entry needed to take and put it there. Not because mystical reasoning has overtaken his mathematics, but because the alternative, that the entry happens to take its precise required value by accident, has reached a probability indistinguishable from zero. This is where physics is with respect to the cosmological constant. The accountant has finished the audit. The numbers are on the page. The audit does not, by itself, reveal who set the entry. The audit only establishes that the entry was set, with a precision no random process could produce. The further question of who requires philosophical reasoning rather than additional measurement. The philosophical reasoning is not floating free of the data. It begins where the data ends. And the data, on this question, ends with a parameter whose value is 10 to the 120th times more precise than any other measurement in physics. We turn now to the third claim in the line of foreshadowing. The claim is that because future observers can, in principle, be empirically cut off from cosmic truth, cosmological knowledge is itself only provisional human storytelling, with no privileged claim on reality. The argument runs that if Krauss and Scherrer are right, then observers 10 trillion years from now will be honestly mistaken about the nature of the universe. They will see no other galaxies. They will see no CMB. They will conclude they live in a static, isolated cosmos. They will be wrong. They will be doing legitimate science with legitimate data, reaching the conclusions their evidence supports. And if their conclusions can be wrong, despite being based on legitimate evidence, then perhaps our conclusions can be wrong too. Perhaps the best we can ever do is fit local data with local models, with no guarantee that the models reflect reality. This argument cuts in interesting directions. It is intended by some commentators to undercut the realism of contemporary physics. It is invoked in service of a vague relativism about cosmological knowledge. Examine where the argument actually leads. If the argument is taken seriously, it does not undermine theistic conclusions. It undermines naturalist confidence in present cosmological realism. If future observers will be mistaken because their evidence is incomplete, then the same logic could apply to us. Our own evidence may also be incomplete. The apparent self-sufficiency of the universe, the apparent absence of any need for a transcendent cause, may itself be a parochial inference from a limited dataset. Krauss and Scherrer's result, applied symmetrically, is corrosive to any worldview that assumes present visible evidence exhausts ultimate reality. It bites equally on theism and atheism. Notice which worldview is more committed to the assumption that present visible evidence is the whole story. Naturalism, in its strongest forms, identifies reality with what science can detect. If detection is in principle time-bounded, then naturalism's central claim that the world consists of what science can find is in trouble. Theism, by contrast, has always held that ultimate reality includes elements that exceed empirical detection. The cause of the cosmos, by the nature of the case, is not a thing within the cosmos. Whatever set the initial conditions, configured lambda, established the laws of physics, is not located inside the system whose laws and conditions it set. The Krauss-Scherrer result, far from undermining theism, illustrates the theistic point. Truth can outrun evidence. Reality can exceed observability. The universe can contain features that are inaccessible to observers operating from within it. The argument intended to undercut all cosmological realism turns out, on examination, to favor the framework that distinguishes ontology from epistemology. That framework is theism. The framework that conflates them is naturalism. The conflation is precisely what the Krauss-Scherrer scenario punctures. What does it mean that, when future observers will be honestly mistaken about cosmic origins, the worldview that survives the puncture is the one that always insisted reality is larger than what can be measured? This is the part that stays with me. Not the scale, the asymmetry. Truth remains true even when evidence becomes inaccessible. Reality is not a function of the observer's epistemic state. The cosmos that future observers will fail to perceive will still have existed. The Big Bang will still have happened. The other galaxies will still have been there. The CMB will still have been emitted. None of that vanishes because the data is no longer locally available. The world is what it is, regardless of what a given epoch can detect. That is, as it happens, a deeply theistic conviction. It is also what the equations confirm. Now consider the cosmological argument applied to this topic specifically. The cosmological argument, in its classical form, runs that everything that begins to exist has a cause, that the universe began to exist, and that therefore the universe has a cause that is itself uncaused, eternal, and existing independently of the universe. The argument is deductively valid. Its premises are defensible. The first premise reflects a near universal feature of human reasoning, that things which come into existence do so for reasons. The second premise is supported by Lambda-CDM cosmology itself. The standard model has the universe beginning at a finite time in the past, roughly 13.8 billion years ago, in a hot, dense state from which the expansion began. The universe is not eternal in the past, it is bounded. The conclusion follows. Whatever caused the universe is itself uncaused, eternal, and existing independently of the universe. It is also, by the structure of the argument, before space and time, since space and time are features of the universe that began with it. Whatever caused the universe is therefore not in space and not in time. It is also extraordinarily powerful, since it brought into being everything that exists. It is also, given the fine-tuning of physical constants, extraordinarily knowledgeable, since the configuration that resulted is one out of a vast space of possibilities, and the chosen configuration permits the existence of a structured cosmos containing observers. Power, knowledge, will, since a choice was made among possibilities. The cause of the universe has the attributes that classical theism has always ascribed to the Creator. Notice what is not happening here. We are not reasoning from gaps in scientific understanding to a divine cause. We are reasoning from the structure of the equations themselves. The Friedmann equations have a beginning. The cosmological constant has a value that fits no theoretical prediction. The fine-tuning of multiple parameters places our universe in a vanishingly narrow region of possibility space. These are features of mainstream physics, not features of fringe argumentation. The conclusion that the universe has a cause with power, knowledge, and will is not a desperate retreat from science. It is what the equations actually point toward when one reads them honestly. The materialist has, at this point, several possible responses. The materialist may say, the universe might be eternal in some way that the standard model has not yet captured. Perhaps before the Big Bang there was something else, and that something else has always existed. This is a coherent response. It is also unsupported by current data and, by its own admission, beyond present observation. The standard model has the universe beginning at the Big Bang. Models of pre-Big Bang physics, eternal inflation, cyclic universes, conformal cyclic cosmology, ekpyrotic models are speculative extensions, not established physics. They may turn out to be correct. They may not. As of this exploration, they are hypotheses, not data. The materialist may alternatively say the universe might be self-causing, deriving its own existence from the laws of physics themselves. This response treats the laws of physics as somehow prior to and independent of the universe they describe. Laws of physics are descriptions of how the universe behaves. They are not entities capable of producing universes on their own. The proposal that mathematical regularities have causal power on their own, separate from any underlying reality they describe, is a Platonic metaphysics that few physicists would defend on reflection. It is also, on examination, a kind of theism in disguise, replacing a personal creator with an impersonal, eternal logos. The structural form of the argument is preserved. Only the personal aspect is removed. And the personal aspect is precisely what the fine-tuning evidence, with its appearance of choice among possibilities, suggests is required. The materialist may finally say, "We do not yet know the answer, but science will eventually figure it out." This is the response that has been deployed for the deepest questions in physics for at least a century. It is sometimes correct. It is sometimes a placeholder. The cosmological constant problem has been with us since the 1960s. The Hubble tension has been with us since the 2010s. Dark energy's identity has been unknown since 1998. NASA's own dark energy materials, written by working scientists, say the short answer is, we do not know. The promise that science will eventually resolve the deepest cosmological questions is, at this point, a promissory note that has been outstanding for a long time. It may be paid, it may not. Investing one's metaphysics in a future that may never arrive is a kind of faith. It is the kind of faith that materialism specifically claims not to require. The hidden assumption that purely natural mechanisms must, in principle, exhaust reality is itself a metaphysical commitment, not a scientific result. What does it mean when the most committed naturalists claim that science will eventually explain everything is itself a non-empirical assertion that cannot be tested by science? Take a moment to sit with that. The claim cannot be examined by the method it endorses. The claim is therefore self-undermining on its own terms. The cosmic prison, in the end, is not what materialism says it is. Materialism reads the prison as a metaphor for cosmic indifference, for the absence of meaning, for the irrelevance of conscious life. A closer reading reverses the metaphor. The prison is what the equations of an accelerating universe predict. The equations rest on parameters whose precision exceeds any precision we have ever measured. The precision exceeds by many orders of magnitude any plausible appeal to chance. The precision is associated with the existence of structure, the formation of stars, the assembly of galaxies, the support of observers. The prison exists because the universe was configured with the values of constants that permit a universe to have observers in the first place. The prison's most striking feature, that future observers will be cut off from the truth of cosmic origins is itself a reminder that truth is not equivalent to current observability. Reality exceeds evidence. Knowledge is not the limit of being. The prison is real. The prison is built into space-time. The prison's architecture confirms rather than refutes the conclusion that whatever set the initial conditions of the cosmos did so with intention, knowledge, and the capacity to choose among possibilities the one configuration in which a structured universe could arise. Earlier, I said we live in one of the few epochs in which the universe can be correctly inferred from observation. Think about that for a moment. Of all the epochs since the Big Bang, of all the eras to come over the next 10 trillion years, we sit in a brief window during which the cosmos can still tell its own story. Earlier epochs lacked the technology and, in some cases, the existence of observers. Later epochs will lack the data. We are the brief flame between the dark and the dark. The window is not random. The window correlates exactly with the period in which intelligent life can examine its surroundings and reach correct conclusions. What does it mean that the cosmic timeline has, embedded in it, a narrow band of time in which truth is recoverable, and that we are in it? Let me bring this exploration to a close. We began with a number, the cosmic event horizon at 16.7 billion light-years, the boundary beyond which no signal sent today will ever reach us. We followed that number into the structure of lambda-cold dark matter cosmology, distinguishing the particle horizon, the Hubble radius, and the event horizon, three boundaries that do different things and mean different things. We examined the discovery of cosmic acceleration in 1998, the rehabilitation of Einstein's cosmological constant, the construction of the modern dark energy framework, and the precision measurements of COBE, WMAP, and Planck that pinned down the parameters of the model. We examined the calculations of Krauss and Scherrer, who showed that future observers will be fundamentally incapable of recovering the true history of the universe, because the empirical evidence will have receded beyond detection. We examined the simulations of Loeb and Nagamine, which show that the visible cosmos collapses in cosmic time to a single merged local group remnant surrounded by silence. We examined the open problems of mainstream cosmology, the cosmological constant problem identified by Weinberg, the Hubble tension confirmed by the H0DN consensus in 2026, the unidentified nature of dark energy that NASA itself admits cannot currently be explained. We followed these threads to the present observational frontier, the Dark Energy Spectroscopic Instrument, and its 2026 completion of the planned 5-year map, Euclid's deep field observations of galaxies beyond 10 billion light-years, and the careful caveats that, while the prison's existence is robust, the prison's exact future architecture depends on the still unresolved nature of dark energy. We then examined the philosophical claims that some commentators attach to this physics. We considered the argument that cosmic vastness implies meaninglessness, and we found that the argument depends on a hidden premise about scale and significance that nothing in the equations supports. We considered the argument that physics's success in describing acceleration eliminates the need for a creator, and we found that description is not explanation, that the dominant component of the universe remains unidentified, that the cosmological constant problem represents a precision exceeding any precision in any other measurement in physics by many orders of magnitude. We considered the multiverse proposal, and we found that it lacks observational evidence, that it does not eliminate the explanatory question, but only relocates it, and that its motivation is itself an admission of the fine-tuning it tries to dissolve. We considered the argument that future epistemic limitation undermines all cosmological realism, and we found that the argument cuts more deeply against naturalism than against theism, because theism has always held that reality exceeds observation, while naturalism, in its strongest forms, has not. The evidence, examined honestly, points in a direction that the equations themselves suggest. The cosmos has a beginning. The cosmos has constants set with precision no theoretical prediction can match. The cosmos is configured to permit the existence of observers in a narrow window of cosmic time. The cosmos exhibits structure, intelligibility, mathematical regularity, and a delicate balance of parameters that, on every alternative account, requires extraordinary coincidence to have arisen. The conclusion that an intelligent cause stands behind these features is not a leap. It is what the data, examined without prior commitment to materialism, naturally supports. Power, to bring the universe into being. Knowledge, to configure constants with the required precision. Will, to choose among possibilities the configuration that permits structure and observers. These are the attributes the evidence implies. They are also, as it happens, the attributes every classical monotheistic tradition has ascribed to the Creator. The cosmic prison, in the end, is a feature of a universe whose architecture points beyond itself. The horizon does not refute the Creator. The horizon is a reminder that reality is larger than observation, that truth persists even when evidence does not, that we live, briefly, in one of the few epochs from which the cosmos can be honestly understood, and that the configuration permitting that understanding is itself a feature requiring explanation. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. Sleep well tonight, knowing that the prison surrounding you, with its silent horizon and its receding galaxies and its eventually invisible afterglow, is built into a cosmos whose precision, whose intelligibility, and whose narrow window of recoverable truth all point in the same direction, toward a cause whose attributes the evidence has all along been quietly describing. Good night.